Good. So my name is Shuji Tanaka again. I'm from the Tohoku University, Sendai, Japan. So today I will talk about the latest MEMS. Maybe in my lecture, you can find surprising, astonishing technology of MEMS, and it's very broad applications from your daily life to the industrial systems. So maybe all of you are using the smartphones. So smartphone is different from the old style phones. So what is different? Main difference is it's so interactive. So in what situation do you think your smartphone is interactive? Maybe I think gaming. Okay. So for this example, if you incline your smartphone, you can drive the car in the game. So this smartphone has some function to measure the rotation. Maybe this is very famous, I believe. Pokemon. Okay. So Pokemon is really interactive because it's something like the simple AR. So the backside, you can see the real image of the taken by camera, and it is the Pokemon is overlapped on these images. Actually, the Pokemon game works without sensors, but it's very pity. Something like this. It's the backside is just a simple image. So the MEMS, so something like sensor, is making this Pokemon game is so attractive. So what kind of sensor is used to make the smartphone so interactive like this? This is MEMS inertial sensors. Okay, inertial sensor measures the acceleration or the rotations. Oh, so this example shows the MEMS accelerometers. The mechanism or the principle is so simple. So let us consider this kind of system. So here now the boxes and on the trailers, and he's pushing. So if he pushes the trailer so fast, what happens? Maybe this box moves and fall down. Such things happens. So this kind of principle can be used to measure the acceleration. So please consider this kind of simple system. Now the mass is fixed on the trailer using the spring and dashboard. And if we push the trailer like this, maybe you can imagine that this mass moves. And the motion of the move is depends on the acceleration you apply to the trailers. So by measuring the motion of the mass on the trailer, so you can measure the acceleration. This is a very simple principle of the accelerometers. Of course, to understand the motion of the mass, you need to know the physics of the dynamics. So now we return to the MEMS accelerometer. Oh, the principle is the same like this. The mass is here, okay, and mass is suspended by the springs here. Here two springs. So this mass moves right and left, depending on the acceleration applied to the system. The mass motion can be measured by this mechanism. If the mass moves, the gap between the mass and this finger changes, and this change is capacitively measured. Actually, the MEMS is a very, very small system like this. The size, maybe this is 0.5, not point, this is 0.5 millimeter or even smaller. So 0.2 millimeter or something like that. So that this gap is about 0.1 1 micron to the 3 microns. So small gap. So this is a principle of the accelerometer. And your smartphone has this accelerometer, so it's interactive. How to measure the rotations? The rotation can be measured by the gyroscope. Okay, so this shows us a principle of the gyroscope. Now, mass is suspended in X direction and Y direction using the springs. So now we drive the mass to the X direction. So this mass vibrate like this in X direction. And if the angular velocity, so rotation is applied to this system, this mass start to vibrate also in Y direction because the Coriolis force works in Y direction. And this Coriolis force is proportional to the angular velocity applied to the system. So by measuring the displacement of the Y direction, the angular velocity, so the rotation speed, can be measured. This is a principle of the MEMS vibrometry gyroscope. And this kind of gyroscope is used in your smartphone or the gaming system and also automotives. So for this example, this car has a MEMS gyroscope and measure the yaw rate. And if the the road is so slippery by snow or the ice, yeah, the spin will happen. But the sensor can detect the spinning of the car and compensate by controlling the brakes at the four wheels. So this is a photo of the real gyroscope developed by Toyota Motor and Tohoku University, our university. So you can see the mass here. Here's mass, and they are supported in X direction and Y direction using the springs. So the system is really like this. So now let us compare the real die and this principle. So what is the main difference? Okay, the main difference that in principle we need just one mass, but actually this sensor has two masses. So this is a big difference. Why do we need two masses? There are two or three reasons, but now I explain important one reason. You know this one. Maybe you used or that you saw this kind of equipment in the music class in your school. So yes, this is a tuning fork. If you hit the tuning fork like this, so very clear sound, the A sound continues very long time. So maybe you know this one. So the tuning forks has two beams, one beam and two beams, and connected at the supporting part. Why do we need two beams for tuning fork? There's a reason. If there's just one beam, yeah, we can hear the sound, of course, but the sound doesn't continue so long time because the vibration energy dissipates into the supporting box. So mechanism like this. So this is a beam. Now we consider the one beam. If we hit the one beam, okay, the beams vibrate and we can hear sound. But the vibration energy easily dissipate into the substrate and the sound may stop in a short time. Tuning fork, there are two beams, as I explained. It vibrates like this, close, open, close, open. This kind of motion is generated. So the stress or the deformation at this part can be cancelled because this is the right side and this is the left side. So that at the supporting part, two displacement can be cancelled. So no vibration force dissipate into the substrate. Okay, so the sound continues so long. That is one reason why need two masses for the vibrometry gyroscope. Of course, there's other reasons. By using the two masses, it can sensitive, and also it can be uh, robust against the external, the acceleration or the shock. So this is the disassembled sensors, and this sensor is called the combo sensors. Okay, why we call combo sensors? Because this sensor include the accelerometers and the gyroscope. The left side is the twin-axis gyroscope, as it's a rotation sensor. And the right side is accelerometers. There are twin-axis accelerometers, x-axis, y-axis, and z-axis. I already explained the x and y-axis accelerometer, how it works. And this is a twin-axis gyroscope. Maybe it's very complicated structure. It's not so easy to understand how it works. Okay, but this complicated structure can measure twin-axis rotations. The motion is like this. So as I explained, to measure the rotation, first we need to initiate the vibration. Okay, and the vibration driving is this red arrows. So this kind of motion. Okay, this red arrow vibration is initiated. The driving. And when the system is rotated, three axis, so yaw, pitch, roll, three rotation we can consider. And if the yaw rotation around the z-axis is applied, uh, this part vibrate up and down. Okay, and by measuring this vibration, we can know the yaw rotation. And pitch and roll rotation can be measured using the different mode of the vibration. So roll can be measured by this orange vibration, this kind of, yeah, actually this vibration. And pitch can be measured by this vibration. So using the one structures, the three-axis rotation, angular velocity can be measured. Actually, this is the MEMS installed in the iPhone 15. Okay, the iPhone is one of the most expensive, one of the most the highest end smartphone, as you know. And the MEMS gyroscope sensor is here. Okay, this black small one. It is a 6-axis combo sensor, accelerometer plus gyroscope. Actually, this sensor is quite nice sensors. The very famous company, Bosch Sensor Tech, this is a German company, is making these 6-axis inertial sensors. It's a bit expensive, good sensors. Why iPhone is selecting this good sensor, not cheap one? Yeah, there's a reason. Actually, if we take the sensor is like this. So it's just a black, some parts, maybe the size is 3 millimeter, 4 millimeter, something like this. Thickness is 1 millimeter, and it's covered by the black plastic. This black one is a plastic. And the plastic is protecting the sensors. Okay, but the plastic and the sensor, this is made of the silicon, has a different thermal expansion coefficient. So if the temperature increases, compared to the silicon, the plastic expand a lot. That creates some stress into the sensors. Okay. And if the moisture increases, the humidity increases, plastic absorbs the humidity. Okay. And this plastic expands a little bit. It's a swelling a little bit. This also uh, stress the sensors, and the sensor may change the sensitivity or the 0 biases. This is not good. Okay. So we want to avoid this kind of the instability in the real use. And the high-end MEMS sensor has a good structure to avoid this kind of the problems. So this is a bit special topics, a bit difficult, but so maybe you can understand the two different of the structure of the sensors. Left side is this is a very simple structure. So now it shows a Z-axis sensor. Z-axis sensor is like a seesaw. Okay, there's a mass and it's supported like this. And right side and left side, the length is different, so the weight is different. If z-axis acceleration, this direction, is applied, this seesaw inclines because this is not balanced. And this angle, inclined angle, can be measured using the two electrode on the cap wafers. So, but this is a very reasonable structure, easy to understand, but there's a problem. So, as I explained, there is a plastic on the cap wafer, black plastics that protects the sensors. And if the plastic deforms by temperature change or the humidity, the cap is pushed or the pulled, and the gap between the electrode and mass slightly changes. That changes the sensitivity or the 0 bias. So the sensor is not very stable in the different conditions. This is a very good sensor, actually the Bosch sensors. So the principle is same. There is a mass. This is a seesaw structure, but the structure is very symmetric. Right and left side, same length. Only the difference of the mass. Right side is a bit heavy. And this angle, inclination angle, is measured by the electrode, but this electrode is fixed at the center point of the supporting point. Okay. So even the cap is pushed by the plastic, but the sensor part doesn't affect a lot. So it's pretty stable. And that is why the Apple is using this sensor for their high-end smartphones. But clearly, comparing the two structures, this is more difficult to make, complicated. So how to make is a problem. Actually, this was made like this. So this is a silicon substrate. So maybe 20 centimeter diameter was a silicon substrate. And on it, the electrode, sensing electrode is patterned. And on it, the blue part is a sacrificial layer made of the silicon dioxide. And some sensor structure is fabricated using the very thick silicon, polysilicons. And the gap is filled with another silicon dioxide. And then this part is removed by silicon etching. And on it, another thick polysilicon is deposited. And then finally, the blue part, this is a sacrificial oxide, is removed by some chemicals, the vapor HF. And we can make the two stories of the microstructure. So this is made by the two story of the structure. This is one story. This is the two stories of the. So the complicated structure can, and we can achieve the very good performance, very good stabilities. By the way, so the if that application of the gyroscope is not only smartphone or the automotive, but also there are other applications. So this shows the application of the high performance gyroscope. Clearly, automatic driving car is a very important applications. And the autopilot drone in building may be important. In the outside, the drone can receive the GPS signals, but inside the building, it's impossible. This must be autopilot using the inertial sensors. And for you, maybe this is more easy to understand, but VR headset. So now we can enjoy the VR headset in front, in by just by sitting, okay, or just standing. But we cannot walk around in the some spaces because VR headset doesn't have the position tracking function. Of course, some VR set expensive VR set has a poor position tracking system, but it uses a IR head house here, and this IR infrared light is detected by many IR sensors here. So only she can move around maybe 2 meter by 2 meter, something like that. We cannot enjoy the VR in the big space because the performance of the gyroscope is limited. How the performance is limited? So you can see this example. This is a student experiment. Now there is a 50 centimeter, the squares. And on it, the student follows these trailers 2 times. And this trailer has a MEMS gyroscope and MEMS accelerometers. After running the trailer 2 times following this the squares, the data is taken out and the trajectory is reconstructed based on the measured data. And the reconstructed trajectory is like this blue one. It's pretty much different from the real motion because the performance of the gyroscope is limited. Actually, this this chart shows the performance of a comparison of the performance of the different types of the gyroscope. Left side is a low-end gyroscope, so the low performance. Low performance gyroscope is always MEMS gyroscope. On the other hand, right side is a high-end gyroscope, mainly for the very special military use. The performance is maybe 10 to 6 or the 10 to 7 times different. Also, the price is so different. Maybe this is, I don't know, maybe a few RMB, I think, my 5 RMB, something like that. But this is, of course, very, very expensive. Maybe we cannot purchase it one. And the middle range is this is an optical gyroscope, which is now used for the automatic driving. But the price is still very expensive. So we want to replace this kind of very expensive fiber optical gyroscope or the ring laser gyroscope. They are all optical gyroscope by MEMS gyroscope. By improving the MEMS gyroscope performance, there are many methods to improve the MEMS gyroscope performance. But I will introduce just one method that we are now trying. So, you know this one. This is the Foucault pendulum. So here you can see the steel ball. Okay, steel ball is suspended by the wire, thin wire here, and it vibrate. Okay, actually this photograph was taken in the German museum. Okay, and this vibrate, and the vibration direction is gradually changing. Why? Maybe you know because the globe, Earth is rotating. So this Foucault pendulum is a sensor to measure the rotation of the Earth. Okay, and the rotation of the Earth is so slow but such a very small, slow rotation is also precisely measured by the Foucault pendulum. Okay, so this is a good gyroscope. Okay. By the way, I will ask one question. So why the Foucault pendulum doesn't stop? It's always vibrating. So when you go to the museum, it's always vibrating. Of course, there is a friction, air frictions. So the energy is dissipated. And if we wait for long time without the driving, the, the amplitude of the Foucault pendulum gradually getting smaller and smaller and finally may stop. But when it always the Foucault pendulum is vibrating. Why? What is the mechanism? Someone is pushing the mass like this? Maybe no. So actually the system is like this. On the seal, okay, there is such kind of mechanism. And this mechanism is slightly pulling the wires. The important is this motion is the twice the frequency of the pendulum. So the frequency is twice. So at the twice frequency of the pendulum, the wire is a little bit pulled. So the length of the wire is slightly changed. This excites the vibration. This is called the parametric excitation. Okay. So now we want to make the Foucault pendulum into the very small system using the MEMS technology. Okay. So actually, we cannot suspend the small mass into the MEMS system. So what we use the same system, the mass is suspended to axis by the springs. So if the rotation is applied to the system, the vibration in X direction and Y direction is coupled via the Coriolis force. If the two axes is coupled, the mode is appears. Maybe if you are in the mechanical division, or maybe you run the two-axis system. And if the two axes are coupled, the mode appears. This is a CW mode and CCW mode. And two modes are overlapped. This kind of the linear vibration is obtained because the CW mode and CCW almost has the same frequency, a bit different. The difference is only the rotation applied to the system. Okay, but it's almost linear vibration, but the direction is gradually changing because the two modes has a slightly different resonant frequency, natural frequencies. So this system is now in the MEMS. Actually, we made this kind of system. This is a vibrating mass, and this mass is the X and Y direction. Actually, it's not the physically and X and Y direction, but the in mathematics, it vibrates in X and Y direction. And if it is coupled, CW mode and CCW appears. And we can oscillate two modes independently, but on the same system. So if we overlap two modes, such kind of linear vibration is obtained. And this direction change by the rotation applied to the sensors. What is good of this system? It has a very good stability. For example, even the temperature changes. The sensitivity doesn't change without any compensation. This is quite important for the automatic driving applications, of course. So let's go to another sensors, microphone. So smartphone is of course the phones. So it has a microphones. And the latest smartphone has four microphones because the noise cancellation is done using the multiple microphones. And all microphone in the smartphone is made of the MEMS technology. So you are daily using the MEMS sensor, just calling to your friends or your families. Maybe you are using this one, wireless earphone. We call it TWS earphone, true wireless stereo earphones to enjoy the music. This is not just a earphone. It's a high-tech earphone. It has MEMS accelerometers and also microphones. And if you buy expensive the TWS earphone, that maybe two or three microphone is installed in each side of the earphone. Okay, so why we need a microphone in the earphones? Because because that it is used for the voice recognition. Okay, you can control your smartphone using your voice. So, and voice recognition, the good microphone is necessary. If the performance of the microphone is poor, the voice recognition rate is pretty low. That may be very stressful for you. So now let us consider the performance of the microphone, small microphone. Okay, the structure of the microphone is like this. Very simple. There's a diaphragm. It vibrates by your voice. And this vibration is measured by the fixed electrode, which is called the backplate. Okay. The principle is this membrane vibrates, and this vibration is measured by the backplate. That's all. That is a principle of the microphone. So this is a sensor. So for any kind of sensor, the ratio between the signal and noise is important. This is called the signal to noise ratio or the SN ratio. The SN ratio is high. This is a good sensor. So to improve the sensing performance, we need to decrease the noise, of course. Then what is the noise? That is an important question. So this is used in air. So there is air between the diaphragm and backplate. And this gap is only 2 to 3 microns, very, very small gap. And if there is air in the small gap, the dumping happens, air dumping happens. And this air dumping introduces the noise. Actually, the very, very small random vibration of the membrane. Okay, by air damping, introduce a very small vibration, random vibration of the membrane. That is a noise of the capacitive microphone. It's maybe not very easy to understand in the macro field because the dampers always reduce the vibration in the macro field. Maybe you know this one. This is a car, so the tires, engines, and this tire is supported by the suspension. And this part is a dampers, so dashboard. And dashboard, the function of the dashboard is to reduce the vibration of the wheels. Okay? So in the macro field, the damper is used to reduce the vibration. But in the micro field, the damping introduces the random vibration. Can be understood by the analogy of the electric circuit. So if you introduce a resistor into the circuit, the voltage noise is generated. That is defined by root 4 kV RT. This kind of voltage noise is same in the mechanical system. If you put the resistor, that is the dampers, the small random vibration is generated, but that cannot be felt. That cannot be detected in the macro field because this vibration is so small. But this is a problem in the MEMS field. So how to avoid this kind of problem? So there is a clever guy. So this one. There is a two membranes, okay? And two membranes are connected by the such kind of pillars. By voice, this membrane, double membrane, vibrates synchronously. And the detecting electrode is in between two diaphragms, okay? And this diaphragm makes a closed cavity, and this cavity is now vacuum. So there's no air dumping. because it's vacuum. So it doesn't have the such noise that I explained. So no damping by air gap. So no low noise. And also there are two diaphragm, symmetric structure, differential readout is possible. That result in the high sensitivity. So as a result, the signal to noise ratio becomes very high. So it's a high-end microphone. And actually, this microphone is used so the airports. If you are using the airport, you are using this kind of high-end microphones. This is a real structure. It's already broken by us. So we take now the microphone and disassembled. So this is a membrane, okay? Another membrane is here, but we cannot see. So this is a fixed electrode, and you can see the pillars, small pillars here. These pillars was connecting the top electrode and top membrane and bottom membrane. And originally, this gap was vacuum. For TWS earphone, the TWS earphone is earphones. Of course, the speaker is important. Now, MEMS technology is replacing the conventional magnetic speakers. Like this is one example that we developed with AAC in China. So this is a pretty small the speakers which is driven by the piezoelectric actuators. It is small and it can be used as tweeters and in combination with the dynamic speakers. It's very small and it is actuated only the 1 volt RMS, so we don't need an amplifier. This means this is quite low power. So low power is very important for the wireless earphone application because the battery capacity is limited. And also sound is good because it is a high resolution speakers. It can generate the sound up to the 40 kilohertz. Okay, so very good sound can be enjoyed by MEMS speakers. So this is a smartphone, again, smartphone. Smartphone is also the phone. So you will use this smartphone to talk with your friends and the families. Okay, but maybe the most important role of the smartphone is to connect you to internet. Okay, maybe you are using smartphone to get some information from the internet or to buy something through the internet. Anyway, connecting you to the internet is one of the most important function of the smartphones. The smartphone is communicating with wirelessly, so it's using the electromagnetic wave. So normally smartphone is using the frequency from the several hundred megahertz to the 2.5 gigahertz. So for this range, this range is very useful for the telecommunications. Okay, and in this frequency range, there are so many bands. Okay, about 80 bands. So the different company are using the different bands, okay? Or the different countries use the different bands. Anyway, there are so many bands. And you are allowed to use only the selected band, depending on the phone company. Okay, it depends on the carrier that you contracted. Okay, so the how to select the band which can be used. Okay, this is also done by the MEMS. Okay, this is the front end of the smartphone. So what is the front end? Yeah, maybe you can understand this expression. Here is the antenna. Okay, this is the antenna. Okay, and this is a transceiver. Okay, the signal is processed by these transceivers. So now we consider the receiving the signal. This is called the RX. The, the electromagnetic enters into the antenna, okay? and going to the antenna switches, okay, and then go to the some this orange part and go to the low noise amplifier into the in the transceivers. Okay. And this orange part is called a duplexer and filters. And this is selecting the band that you can use. TX, this is a transmission side. Power amplifier, so the signal is power amplified by power amplifier. And going to this orange part, and going to antenna switch, and then go antennas. Okay. And this orange part is a duplexer and filter. And this separate RX and TX, so the transmission. So this orange part is very, very important. This is, the function is the frequency selection. Okay. The by this filters or the duplexers, we can we can select the band that we can and also separate RX and TX. This we must avoid the signal from the power amplifier go into the RX low noise amplifier. So this is a real chip of this part. Okay. So there you can see the many parts we can call the dies. There are many dies. This one has a 27 dies in the circuit board. And the 80 dies are filters out of 27. So you can understand there are so many filters in the smartphones. And how does the filter works? This is a bit maybe complicated, but the filter works like this. There are resonators, the vibrating structures. The blue and green, the resonators in vibrating structure. So the typical structure of this resonator is like this. There is a piezo film, piezoelectric film, and it vibrates up and down. Okay, it becomes a thick thing. This kind of the thickness extension vibration is generated. So this kind of vibration. And it vibrates. There is a resonance and anti-resonance. As the resonance, the signal go. And as the anti-resonance, signal is stopped. By combining the different resonators like this, we can finally obtain this kind of band pass characteristics. Okay, this is a band which pass the signals. And this here the signal doesn't pass. So it's a rejection frequency. So we can only select the frequency signal in the passband here. Okay, the real structure is maybe like this. This is a vibrating body. So it's a vibrated thickness extension, up and down vibration. Okay, and this vibration body is supported like this by using the cavity. The vibration is separated, isolated from the substrate. So another structure is here. This is a vibration part. And the vibrations part is supported by the so the multi-layer films. And this multi-layer films works as something like a mirrors, acoustic mirrors. So the acoustic vibration is reflected by this structure, and the energy is confined here. So this is a cross-section of the real chip. When we open the chip, the vibrating part, you can see the vibrating part here. It's a bit strange pentagon structure. This is a vibration body. And here is a vibration body. And if the closer look is like this, this is the piezo layer. We call this is the aluminum nitride, the piezoelectric layer, sandwiched by the two metals, and it vibrate up and down vibration. So thick and thin vibrations. Okay. And this is filtering the signals. So in the future, or not only the future, the latest one, the very high frequency is used. The very typical example is the 5G. This is the N77 and the N79. This is a 5G band. And Wi-Fi 6E, this is also new Wi-Fi, located at a very high frequency. So to use this kind of band, high frequency filter is necessary. And in the future, maybe we will use further higher frequency to accommodate the communication data. And to make the higher frequency vibration, the higher frequency filters, we are now studying this kind of structure. This is a very, very thin lithium niobate, the simplate, suspended simplate. And we make this kind of electrode, and this structure can vibrate very, very high frequency, 5 gigahertz frequency. And you can see the clear, the signal, the resonance and anti-resonance. The difference of the impedance at resonance and anti-resonance is very important for filters, because the filter is a passband and rejection. This ratio is very important. Okay, so I explained the gyroscope or the filters, the microphones. They are all vibrating systems. Okay, so this is a vibration. It's a stroboscopic movie of the resonating wine glass. So it's vibrating is like this. So if vibration often result in the big problem, okay? This problem is a fatigue problem. So if the material or the structure is always vibrating, the fatigue happens, and finally the structure is broken, okay? Yeah, this problem is the typical the accident by the fatigue is here, plane crash. This is a plane called the Comet Mark 1. Comet Mark 1. This was developed by the de Havilland. This is an England company. Okay. Actually, this is a world first jet airplane. Jet airplane is flies maybe very high, 10,000 meters high. Okay. So in 10 meters high, the pressure is low. Okay. So in the land and the 10,000 meter high, the pressure is so different. So when flying, the cabin is pressurized. So if the airplane is going up and landed and going up and landed, this kind of pressure is applied to the cabins repeatedly. Okay, and this vibration, this force, this repeated force generates the fatigues, and the crack is generated here. It's a window here, or that the antenna window, and finally the cabin is broken, and unfortunately the plane crashed 3 times in the very short period. Plane crash in May 1955. Also, of course, all passengers were killed. And the next, the January 1954 and April 1954, all passengers were killed by this crash. And only this airplane flights, this times, 1,000 flights. Of course, this was tested before making the airplane. The cabin was tested, but the testing method was not good because of limited knowledge in this year in this age. Now the engineers, the de Havilland England engineers solved this problem. Now we don't have this kind of problem. Anyway, by repeated vibration, the structure is broken. But MEMS always vibrate, but not broken. You can use a smartphone every time. This is a very, very early MEMS, world first surface microfacial method. It was presented in 1965, very, very old, world first vibrating MEMS. Actually, this is a filters. The principle of the filter is very same that I explained for smartphone for RF front end. But in this age, this device was not commercialized. That's not practically used because fatigue problem. This cantilever is made of the electroplated gold, and by vibrating this gold is fatigue, and finally frequency change, and maybe finally this cantilever vibrator broken. Now, why we can use the MEMS without this kind of fatigue problem? The importance of the material. We are now using the silicon, single crystal silicon or the polycrystal silicon as a structural material of the MEMS. And the silicon is actually the fatigue-free materials. So this is one of the experiment. So this is the vibrators. And at the supporting area, there is a notches like this. So if this vibrate, the very strong stress is applied to this notch. And by repeating this fatigue happens and this part is broken. But if it is made of the silicon and tested at a certain condition, the this MEMS structure doesn't break. So in this example, 1.5 gigapascal is applied here, and it is tested under the room temperature, 50% relative humidity. So no vibration changes, the test interrupted because nothing changed. Here, the further higher stress, 2.55 gigahertz is applied. So in this case, the vibration frequency a little bit decreasing because the crack is generated here. And finally, the structure is fractured like this. So other example, this case, the environment, the humidity was changed. The humidity is low and high. So this is the 50%, the humidity is low. When the humidity is low, the frequency doesn't change. The humidity is 50% high, the frequency decreases because the crack is propagating. And finally, maybe it breaks. Okay. So what we found, silicon is almost fatigue-free in dry environment at low temperature, at room temperature. Okay, so if we use silicon as a structural material, we don't need to care the fatigue problems. And now the very big in this test, very big stress is applied 1.5 gigahertz, 2.55 gigahertz. Actually, this is a very big stress. So I can explain like this. So steel. So many things are built by steel, car, bridge, buildings. So most of the machines are made of the steel, okay? And this is typical steel, SS400. SS400 has a tensile strength, minimum tensile strength is 400 megapascal, okay? So you can understand 1 gigapascal or the 2 gigahertz pascal is a very, very big cell that can, under such a stress, that still cannot survive. So maybe so in China, so you can often see this car. This is Xiaoping, the G9s. Okay, Xiaoping G9 has two sensors called the LiDAR sensors. This and this right side and left side, two sensors. What is a LiDAR? LiDAR is a scanning laser, light detection, and range finding sensors. Okay, the laser is scanned, and the distance image can be measured. And this data is used for the automatic driving or the advanced safety control. And laser is scanned by using the scanners. And some LiDAR is using the MEMS-based scanners. So as I explained, even this is vibrating always by big vibration. So that if this is made of the silicon, it doesn't fatigue. So it's very stable. So it's also can be used the automotive. It's automotive. The safety is very, but it can be used. Actually, this is the MEMS riders. It's made by robots, and this is a Chinese company. So there is a TX and RX module. It's a 5 TX and module here. And the light go to and reflected the front side mirror and go to the MEMS micropillar, the vibrating scanners, and go and project to the front side. And light is returned to the same path and going to return to the TX RX modules. By this, there's 5 TX and modules, and it can cover the wide angles. Actually, the field of view is 120 degrees. And this is used for the automotives. Maybe you know this guy, Elon Musk. He has a company, Tesla, the EV company. Okay, he says for Tesla, the LiDAR is not necessary for advanced driving control or the automatic driving. Actually, but this is very questionable. Okay, using just a camera, maybe the Tesla is not so safe. The automatic driving is not perfect. Why Elon Musk say they don't need the LiDAR? So maybe one reason is the LiDAR is so expensive. Okay, but the technology advanced, the price of the LiDAR is getting lower and lower. Okay, this is again the new type of the RoboSense MEMS LiDARs. The structure is more sophisticated and simplified, and the good performance is achieved. But there's a rumor this RoboSense new LiDAR can be purchased just by 1,000 RMB, 1,000 RMB. So 150 US dollar, something like that. Very reasonable cost. Maybe most of it can. If this price is realistic, I think many car can use the MEMS riders. So now I explain the MEMS product, which is either smartphone or the automotive. Not only this kind of application, there are so many other applications and so many other sensors or the actuators. So next I will explain the high-end MEMS, this part. This chart shows this is a consumer application. The bottom is the industry application. And left side, the high volume and the small volume. So now I explain small volume, the high added value, industry application of MEMS. So if you have a question, if you have something to know, maybe you use this one, Baidu, okay? So maybe you ask the question to the Baidu, okay? But in Japan, we don't use Baidu, unfortunately. We use this one, okay? Google, okay? So we ask Google if we have a question, okay? And we ask a question to the Google, the MEMS works. In the data center of the Google, there is the optical circuit switch using the MEMS. This is the fiber, the optical fibers, the optical fiber arrays. The signal is going here to here. And this route can be changed using the MEMS two-dimensional mirror array. So this is a MEMS, this is very small mirrors, and the angle of the mirror can change two axes. And by this motion, the optical path can be switched. Okay, this is a real chip. There are 100, there are 136 there are 176 micromirrors And using the 136 mirrors out of the 176, the optical fiber, optical path can be switched. And each mirror must be controlled, the angle of the each mirror must be controlled. How to do this? The easiest way to consider is to install some sensors in each mirrors. But there are many, many mirrors, 176 mirrors. So if we use so many sensors, the, the structure is complicated, data processing complicated. Actually, the wiring is impossible. So in this case, the angle of the mirror is controlled by vision feedback. The motion of the mirror is monitored by using the cameras, and using the image of the camera, each mirror is controlled. This is a very, very clever way. And this is what the data center is. This is a one row of the data center, and in the one row there are 8 optical switch modules, and one module has the 8 switches, and each switch has a 2 micromirror arrays. So maybe you can understand so many mirrors, MEMS mirrors are working in the Google's data centers. So the MEMS that I was explained has a small structure, micron structure, very, very small, complicated structures. How to make such small structures? Like this? Maybe no, maybe no. This is a lettering on rice. Okay, we cannot make the MEMS like this. Actually, maybe you know the microstructure is patterned using the photolithography technology. Okay, uh, the here is the reticle. This is called a mask. The mask is the small pattern is made on the glass, and the glass is illuminated by UV light, and this is projected using the lens. Actually, there are many lenses, and finally, the pattern is made on the wafers. And by step and repeat motion, this pattern is shrinked and projected on the wafers. And on the wafer, there is a photoresist, and this is illuminated by UV light like this. And the pattern is made like this. By development, the exposed part remains or the removed depending on the type of the photoresist. This is called the photolithography. Using this kind of technology, the microstructure is made on the silicon wafers. Okay. The UV light illumination is here like this, but actually this is not the real. The UV light is not illuminated like that, but depending on the pattern on the reticle, the reticle or the mask is illuminated using by the different direction of the light. Actually, like this, the reticle is illuminated by the different direction of the light. It's a very complex, like, so this is one example here. So very, very complex illumination is used to transfer the mask on the pattern on the reticle to the wafers. And this kind of complicated illumination light is also generated by the MEMS micromirror. Okay, here is this is a micromirror. Each mirror size is 1 millimeter, about 1 millimeter. There are thousands of the mirrors here. And using this mirror, such kind of illumination is used in the photolithography system. It's called the stepper or the scanners. And the stepper or scanner is a lithography system. This is one of the most important tool for the semiconductor industry, and to make the smaller and smaller patterns. Okay, so the lithography tool is getting improved. So the first they use the light eye line light. This the wavelength is at 300 about 350 nanometers, and the wavelength is smaller and smaller. This is the KRF about 250 nanometer wavelengths. ARF, this is about 190 nanometer wavelengths. And recently, the most the lithography system is using the EUV. The wavelength is 13.4 nanometers, very small wavelengths. Okay, the latest EUV scanner is here. Okay, this ASML, the EUV scanner called the EXE 5000 series. Okay, so it's very expensive tools. The price is surprisingly the 2.5 billion RMB. 2.5 billion RMB. Okay, 50 billion JPY. 350 million US dollar. So expensive tool. Okay. The inside is like this. There is a light source. This is a UV light source. And the wafer is here. And the reticle is here. So there's a mirrors. And the pattern is reflected and finally go to the wafers. And pattern is made on the reticles. So maybe you can understand on the reticle, there is a precise small patterns. Okay. And how to make this pattern? Okay. Very small pattern must be made on the reticle. Okay. How to make it? So actually, to make the small pattern with the electron beam, okay, electron beam can be confined, can be focused, very small spot size. And using the electron beam, we can make the small pattern. But if we use just one beam, takes so long that it's unrealistically long time. So we need to use many electron beams. Actually, 26 million electron beams are used to make the patterns on the reticle. And 24.6 million electron beams are controlled by MEMS technology. Here is a aperture array blanking plate which controls the electron beam. This is made by the MEMS technology like this. Okay. So using the MEMS technology, we can make the small, very precise small patterns on the reticle. And this reticle is so expensive. If there is a dust on the reticle, it's a problem. It's no use. So the reticle is protected by the very thin film called the pellicle. Okay, and this pellicle is must be transparent to the EUV light. So we cannot use the polymers, of course. We cannot use metals. So because such kind of material is not transparent to the EUV light. So what we are using is a very thin film, very thin film. This is the pellicle film that is protecting the micro pattern on the reticle. The size is 150 millimeter, about 150 millimeter. But this membrane thickness, suspended membrane thickness, is only 50 nanometer. 50 nanometer. So thin, but suspended. Then how to make it? This is made by the MEMS technology again. So it's the similar technology to make the pressure sensor or the microphone is used to make the EUV pellicle. So this is a summary of my talk. So now I explain some kinds of the MEMS. So you can understand the MEMS are used in the various things around us, smartphone, earphone, or smartwatches, automotives, and the MEMS are connecting the real world and the cyber world. Also, there is a new MEMS application is emerging, like high performance gyroscope, speakers, automotive MEMS radar. There's a new type of MEMS. And that kind of new type of MEMS is emerging endlessly. or more, or the more than 30 years, I think. Not only the daily life, the items, the MEMS are applied to the industrial equipment, such as the optical network system in data centers and the semiconductor manufacturing tool. Okay. Finally, I also explained the some interesting physics in the MEMS field, which is maybe so different from that in the macro field. Maybe I hope you enjoyed my talk. Thank you very much.